Right, this section is zeros of polynomial functions. Let's go over the first theorem we have, which is the factor theorem. It says for any polynomial function f of x, x minus k is a factor of the polynomial if and only if f of k equals 0. And this is a special theorem because when I have the statement if and only if, that means that it's a biconditional statement. You can read this forward and backwards and it is the same both ways. So we could say if f of k equals 0, then x minus k is a factor of the polynomial. Or we could say if x minus k is a factor of the polynomial, then f of k equals 0. So we can use this to be able to factor polynomials of higher degree. If we put in a k and the remainder is 0, that means that k is a 0 of the polynomial, and that means that x minus k is a factor of that polynomial. It divides that polynomial evenly. So with our first example to show this, I want to see if x minus 1 is a factor of this. I can do long division if I want, but since this is a form, a plain x minus 1, I'm going to go ahead and do synthetic division. So set up the synthetic division table here. Make sure that you're not missing any negative signs. We're not missing any terms, so we don't need to put any 0 placeholders. And if x minus 1 is a factor, then we are hoping that 1, once we push it through this synthetic division table, will result in a 0 here. So let's start that process here. Carry down the 3 and multiply up, combine down all the way through. 3 times 1 is 3, negative 2 and 3 is 1, 1 times 1 is 1, 1 and 1 is 2, 2 times 1 is 2, negative 8 and 2 is negative 6, negative 6 times 1 is negative 6, 5 and negative 6 is negative 1, negative 1 times 1 is negative 1, 1 and negative 1 is 0. Okay, so we can say, therefore, since f of 1 equals 0, then x minus 1 is a factor of f of x. So don't just show the work. Write that statement that says what your conclusion is about x minus 1 being a factor. Tie it in with what that theorem says. All right, let's factor this into linear factors given that k is a 0. So they've given us a 0 here of 1. So let's see what we get when we put that through the synthetic division process. I have 2, negative 3, negative 5, 6, and my k is 1. They just outright gave you k. They did not give you x minus the k. So just put the 1 there and carry down the 2 and start your process. Multiply up, combine down, multiply up, combine down, multiply up, combine down. Okay, so if you were to get a problem like this on an exam and you end up with something other than a 0 here, you know you have made an error because it is given that k is a 0. So if we know that k is a 0, why are we even dividing this? We know it's going to end up with a 0. Okay, so not only are we confirming by our synthetic division that 1 is a 0 of that polynomial, but we also have the quotient that's left. So we can partially factor our polynomial as x minus 1 times 2x squared minus x minus 6. All right, now we have this down to a quadratic, and we can factor that. So we'll put a 2x and an x there, and let's do a 2 and a 3 minus and a plus. That would give me my negative 4x plus 3x is a negative x for my middle. Now we have all linear factors, x to the 1, 2x to the 1, x to the 1. And you're finished with that problem. All right, we want to break this down into linear factors as well. So let's start our synthetic division. Make sure that you're not missing any terms. Okay, there's no zero coefficients in there. And k is given as negative 5. Remember, they're telling us negative 5 is a 0, so we should end up with a 0 here when we're finished with this process. Carry down the 8, multiply up, combine down, multiply up, combine down, multiply up, and combine down. Again, we get a 0 there, which is what we should get because it said that the value k given is a 0. So let's rewrite our polynomial as x minus negative 5, which makes it x plus 5 times 8x squared plus 10x minus 3. And now that we have that as a trinomial, we can go ahead and factor that. Let's try a 4x and a 2x and a 3 and a 1, a plus and a minus. That gives me my 12x minus 2x is 10x. And we have it now broken down into linear factors. All right, one of the definitions you had in your at-home notes was the idea of a multiplicity of 0. That's the number of times that a 0 occurs. So on this problem, it says that negative 1 is a 0 of multiplicity 3. In other words, that means that I have x plus 1 3 times. I can divide this polynomial by x plus 1 evenly 3 times. So what is that other factor? Well, think how we could do this. We have synthetic division as a tool we can use. And I can put in a negative 1 through that synthetic division table. All right, we start with the 2. Negative 2, negative 1, 1, negative 8, 8, negative 5, 5, and 0. Okay, so for sure, negative 1 was a 0. Okay, but we know it's a 0 3 times. So in other words, we have this now broken down into f of x equals x plus 1 times 2x cubed minus x squared minus 8x minus 5. And I'm going to try and divide this. We can use the negative 1 in our synthetic division table. Again, just make a new synthetic division table like so. And since it's a multiplicity of 3 and we've only taken out one of those, we should end up with a 0 again here. So let's try that. That's a 2, negative 2, negative 3, 3, negative 5, 5, and 0. Okay, so in other words, I now have this written as f of x equals x plus 1 times another x plus 1, so I can just make that squared, times 2x squared minus 3x minus 5. So this was the second time that the -1 was a 0 of that polynomial. It says 3 times it is, so let's try it again with this trinomial. At this point you could really just do factoring, but we'll just go ahead with our synthetic division. Oh, there's a sign error right there. There we go. Whew, you got to watch those. Don't talk a whole bunch like me when you're doing that. All right, so I now have x plus 1 was a factor. This is the third time we found it as a factor, 3 times, and we're left with 2x minus 5. All right, so we have it factored down into our linear factors, and of course you have to show that multiplicity right there. Okay, the rational zeros theorem. So far we've been kind of babying you when it comes to this work, where we tell you what the zeros are, or that something is a factor. Now they will not be giving you that information. They'll hand you a polynomial and say factor it, or find all the zeros. Okay, so let's think about where these possible factors come from. That's what this theorem is about. It says if P over Q is a rational number written in lowest terms, and if P over Q is a 0 of F, a polynomial function with integer coefficients, then P is a factor of the constant term and Q is a factor of the leading coefficient. In other words, any of the possibilities of zeros that you would want to even try come in the form of P over Q, where P is a factor of the constant and Q is a factor of the leading coefficient. So just to demonstrate this, this is my P, this is my Q right here, and my possible rational zeros come from all the factors of P divided by all the factors of Q. So the factors of -8, what can go into 8? Let's see, we've got a 1, we've got a 2, we've got a 4, and don't forget 8. And Q, just 1. And now it's also the positive and negative of all of those. So a simplified list, it's a little easier to view. We have plus or minus 1 divided by 1 is 1, 2 divided by 1 is 2, 4 divided by 1 is 4, and 8 divided by 1 is 8. And that is our list of possible rational zeros. Now, be careful that you're reading the directions when you do this homework assignment. They haven't asked you to do anything else with this, so just list the possibilities. Don't list anything else. All right, how does this relate to something that we know already? Let's say that I have some polynomial p of x equals x squared plus 7x plus 6. When we've had to factor this in the past, think about how you do that. X and x, plus and plus, let's say 6. Would you try numbers like 7 and 3? Probably not. 3 is okay to try because it is a factor of 6. But 7 is not a factor of 6, so you wouldn't try that. You could try a 2, right? You could try a 6, you could try a 1, but the things that you're trying there are all factors of this. Now this gets a little more complicated because when you have numbers in your lead coefficient that are not a 1, then you've got to be dividing those factors of p by the factors of q. So that's where this theorem is coming from and how it connects to something that you've already done in math. All right, so this is the nature of your problems from this point on. They throw you a polynomial, say find the zeros. So there's no hint of what could be a zero. You have to come up with a list of possibilities. What are the things that you should try? So possible rational zeros, plus or minus factors of the last, so plus or minus 1, 2, 4, 8, divided by factors of the leading coefficient, the factors of the first, 1, 3, 5, 15. Okay, and then go ahead and give a simplified list, your possible rational zeros. The only things that you would want to waste time trying to see if they are zeros is 1 divided by 1, 2 divided by 1, 4 divided by 1, 8 divided by 1, okay, 1 divided by 3, 2 divided by 3, 4 divided by 3, 8 divided by 3, 1 divided by 5, it's quite a list here, 2 divided by 5, 4 divided by 5, 8 divided by 5. We've got a 1 divided by 15, 2 divided by 15, 4 divided by 15, and 8 divided by 15. Whew, it's a lot of numbers there. And don't forget, you have the positive and the negative of all of those. But at least now we know we wouldn't try things like 3. We wouldn't try things like 7. These are the only numbers that could be zeros out of the rational zeros. So let's go ahead and see which ones work. And how do we do that? We do it by synthetic division. So I'm going to put the synthetic division table here, and I'm going to put my first first number that I want to try to see if it's a 0. Okay, and here I have 15. I carry down. 15 times 1 is 15. 61 minus 15 is going to be 46. 46 times 1 is 46. 2 and 46 is 48. 48 times 1 is 48. Minus 8 is 40. And that is not a 0. I happen to know that 2, 4, and 8 are not zeros either, because a theorem that we're not going to actually learn. If you want to look it up, it's called the upper and lower bounds theorem. It's not required, but it says that if you put a positive number through the synthetic division table and you have the line that has the quotient and the remainder has only non-negative entries, then this number is an upper bound. You should not test any numbers that are bigger than 1. So in other words, that means that 1 didn't work for us. It means that 2, 4, and 8 are not going to work for us. It means 4/3 is not going to work. 8/3, 8/5. So we've really narrowed down the list quite a bit just by testing 1. Yes, it was not a 0, but we've really taken down our possibilities of what it could be. Now, I know a lot of us avoid fractions, but 2, 4, and 8 are no possibilities now. Let's go ahead and start on the next number. Let's try the 1/3 and see how we fare that way. All right, carry down the 15. 15 times a third is 5. 61 and 5 is 66. 66 times 1/3 is 22. 2 and 22 is 24. 24 times 1/3 is 8. Negative 8 and 8 is 0. So I know that 1/3 is a 0 of the polynomial. I will go ahead and list that then up here. All right, my zeros. This is different than the possible rational zeros. These are definitively my zeros, not just possibilities. Okay, now 1/3 worked. We know because of the problems that we had before where you have multiplicity, it could work again. So let's see if we can use the quotient that is from this, and see if we can do a little bit of something with that. Well, first off, this is an 15x squared plus 66x plus 24. Once it gets down to a trinomial like this, a lot of times it's easier just to fall back to regular factoring. So I see that I could take a 3 out, and that gives me a 5x squared plus 22x plus 8, and we'll continue to factor. 5x squared is easy to factor as just 5x and x. Let's try a 4 and a 2 there. That gives me here a 20, and a 2 is 22 for my middle. So I found the other factors. How do you figure out what the zeros are from that? Well, let's do the easier one first. If we set that equal to 0 and solve, we get a 0 of -4. If we try this one, set it equal to 0 and solve that, we get an x of -2/5. Okay, so there are our 3 zeros. Now, where did this number go? The 3 that it's in front. It's not a factor, it's a coefficient. We have that number 3 just stretches the graph of this polynomial by a vertical factor of 3, and so it's a little steeper. 3 times as tall and 3 times as deep when you draw it, but it does not contribute at all to what our zeros are. We're still going through the same x-intercepts, so that's all that does. It does change the y-intercept, but it doesn't have anything to do with finding the zeros. All right, the fundamental theorem of algebra says that every function defined by a polynomial of degree 1 or more has at least one complex zero, okay, which means every function can be factored. Even the things that we told you in intermediate algebra class you could not factor, we would say they were prime. They actually do factor, just not with real factors. They factor with complex numbers, the imaginary numbers, if you will. Number of zeros theorem says that a function defined by polynomial degree n has at most n distinct zeros. So if you have a second degree polynomial, you should have at most 2 distinct zeros. You could have just 1 0 for that, but it is a 0 of multiplicity 2 to give you that quadratic polynomial. If you have a 5th degree polynomial, you'll have at most 5 distinct zeros, and so on. Right, the conjugate zeros theorem says that if f of x defines a polynomial function having only real coefficients, and if z equals a plus bi is a zero of f of x, where a and b are real numbers, then z bar, which is a minus bi, is also a zero of f of x. Okay, if you remember, if I am multiplying a plus bi and a minus bi, I'm multiplying conjugate pairs. There we go, conjugate zeros theorem. I'm multiplying conjugate pairs, and what happens is when those multiply, then I get a squared minus b squared I squared, but the I squared is -1, so we get an a squared plus b squared. The I completely goes away, it resolves itself, and that's how those conjugates work together in order to make sure that your original polynomial function has only real coefficients. If you have a complex zero, then you have to have its conjugate is a complex zero as well for the polynomial, if that polynomial has the real coefficients. So here they are giving us the information that 3 plus I is a zero of this polynomial. Find all the other zeros. It's kind of a hefty problem, but I do know that if 3 plus I is a zero, then x minus that is a zero. So it'd be x minus 3 minus I. Remember to subtract the entire zero. It's a binomial zero, so you'll have to make sure that you're subtracting the 3 and the I. But my conjugate zeros theorem says that if 3 plus I is a zero, then 3 minus I is also a zero. That means that I have the factor of x minus 3 plus I. Okay? All right, so now that I have those two complex zeros, I can do some synthetic division, try to find the last one, or you can take the product of those and divide this with long division by that. But let's see where we get with just doing some synthetic division. I know that 1 is a possible rational zero, and it doesn't work for us here. I'm going to, instead of rewriting a whole new synthetic division table, I'm going to do a double line and let's start with 2 is a possible rational zero. 1 times 2 is 2, and I'm taking -4, and 2 is -2. That's -4, that's -6, that's -12, and that is 8. And we're still not quite there. It's okay, you can go ahead and take your time, get some more numbers to test here. Let's try 3 is not a possibility, it's not a factor of 20. 4 is a factor, so let's try 4. Again, 1 is 4, -4 and 4 is 0, 0 and 4 is 0, -2 and 0 is -2, -8, 20 and -8 is 12, and that didn't work. Okay. So we're going to try the next possible rational zero. I know that 5 is a possible rational zero. So let's try it. 1, 5, 1, 5, 3, 15, and 35. And now we've hit a problem here because we have all non-negative entries in that row that contains the quotient and remainder. So nothing bigger than 5 is going to work. My next numbers to try would be 10 and 20. That's obviously not going to work though. So let's go ahead and try some of the negative numbers. So where this goes. You can see here we're going to be doing synthetic division quite a lot. So you want to be pretty efficient at it. All right, let's try a -1 now. So 1, -1, -5, 5, 3, -3, 17, and that doesn't work. So we will try a -2, and looks like -2 is the winner. So the zeros will list nicely are a 3 plus I, 3 minus I, and a -2. Okay, list them nicely and put a box around it. Got quite a bit of work to show on these, so you want to make sure your answer gets seen. All right, let's find the zeros and all of their multiplicities here. So here I have a -1 is a 0 with a multiplicity of 2. So -1 with multiplicity 2, a +1 with the multiplicity of 3 coming from that, and x squared minus 10, the way we find its zeros is to set it equal to 0 and solve. So I'm going to use the square root method. So x is plus or minus the square root of 10. So negative square root of 10 with a multiplicity of 1. And square root of 10 with the multiplicity of 1 as well. Okay, and then I have another problem here. 5x squared, if that was set equal to 0, we would get x equals 0. And so 0 is a 0 with multiplicity of 2. Here I have x squared minus 16, so that would give me 4 and -4, multiplicity 1, multiplicity 1, and then a -5 with a multiplicity of 1. That's all they're asking you to do on this, is just find the zeros and the multiplicities. All right, find a polynomial function of least degree having only real coefficients and zeros as given. I'm going to look at the numbers here, and I see the first one that's listed is a complex number, but we want a polynomial that has only real coefficients. If I have a polynomial that has only real coefficients and you have a complex zero, then its conjugate, which is 3 minus 2i, is also a zero of that polynomial. All right, so we need to find that function. We'll say x minus 3 minus 2i and x minus 3 plus 2i. That is making the factors out of those two zeros. And then I have x minus a -1 and x minus 2. And it's going to be easiest if you view this way. This is a something minus 2i and something plus 2i. Something that's of that form is going to be conjugate pairs, so we don't have to multiply out these things and get 9 terms out of it. We can just do a simple x minus 3 times x minus 3 is going to be x squared minus 6x plus 9. And then we're subtracting the, sorry, don't put that parenthesis there. We're subtracting the 4i squared. So we're subtracting 4 times -1, so it'd be a plus 4, which makes this a plus 13. Okay, so that's all of this multiplied together. And then I'm going to take this and multiply that together. I get x squared minus x minus 2. Now we just have these two polynomials to put together, to multiply together and collect like terms. So I have x to the 4th minus x cubed minus 2x squared minus 6x cubed minus about positive 6x squared and a positive 12x. Then plus 13x squared minus 13x and minus 26. Combine like terms, I have x to the 4th, and you can put some kind of a marker under these as you do them so that you can keep track of what you've used. And I have negative 7x cubed. I have negative 2x squared, positive 6x squared, that makes a 4x squared, plus 13x squared is a 17x squared. I have a 12x and a minus 13x, that's a negative x, and my negative 26 at the very last. And they've already named this as f of x, so we'll say f of x equals. And that's it. You go ahead and try your homework. Let me know if you have any questions on this, and send me a message or give me a call. Thanks. Bye-bye.